Okay, welcome back. We got more to do with slope, okay? More with lines 1.5, more slope. We have to deal with parallel and perpendicular lines and looking at the slope of those guys. So I'll symbolize parallel with the railroad track symbol and perpendicular with the upside down T. So first off, if you have parallel lines, that implies that the slopes will be equal. Okay? And there's always an issue like, okay, a vertical line doesn't have a slope, so we can't technically say that the slope of two vertical lines are equal. So you have to make an extra part of your definition. We're just going to leave that out though, okay? In general, most of the time, 90% of the time, this will imply the slopes are equal. Part B then, if you have perpendicular lines, that's going to imply that the slopes are negative reciprocals of each other. So slope 1 will equal -1 all over slope 2. But also you can think of this as saying when you multiply the two slopes, m1 times m2, this will result in a -1. Okay, so the first set of problems are kind of like puzzle problems again. They give you some information and they want you to find the equation for the line in slope-intercept form. Okay? So number 5, they're telling you the line passes through the line such that we want its equation is passing through the point -8, -10. And then the line is parallel to y equals -4x plus 3. Okay. So to do our equation of a line, we're going to need a point and a slope. So first off, the point is given, right? So the point is given as -8, -10. So we have that down. Secondly, we want to find the slope. And because we know our line is parallel to this line, it tells us that it will have the same slope as this line has. So the slope of this line is -4. So maybe we can say the slope of the given line, m1, is -4. So the slope of our line that we desire, we'll call that m2, must also be -4. And it's all because it's parallel to this line right here. Okay, once you've established that information, you can go to your point-slope form and get your slope-intercept form accordingly. So let's go ahead and do that. I have then y minus y1 is -10 equals the slope -4 times x minus x1, which is -8. I'm simplifying, so y plus 10 is -4 times x plus 8. Distribute the -4. Okay, so you'll have y plus 10 equals -4x minus 32. And then you'll have y equals -4x minus 42, and then that's it. Okay, let's keep on going and look at some more examples. Here's problem 8. So this time our line is passing through the point -4, 2. The line is perpendicular to the line y equals 1/3 x plus 7. So again, first we need a point, and the point is given as -4, 2. And then secondly, we need a slope. And to get the slope, we note that the slope of this line is 1/3, right? So the slope 1 is 1/3. And then our slope, then, we can find by just taking the negative reciprocal of 1/3. Okay, so to get the negative reciprocal, you flip the original and then you make it negative. Okay? So our slope must be negative 3. Okay, so for our equation, we'll have y minus y1, which is 2, equals negative 3 times x minus negative 4. Simplify this stuff, so y minus 2 is negative 3 times x plus 4. Then we'll have y minus 2 is, distribute the negative 3. So you'll have negative 3x minus 12. And then add the 2 to the other side. So you have y equals negative 3x minus 10. Okay, let's look at a more complicated version where the equation is not given in slope-intercept form. So this problem is considered easy because all you have to do is look, and there's my slope. And the next problem, that's not the case because the equation is given in general form. Okay? So in number 10, we're told the line we want passes through the point negative 1, 3. And then also our line, we want it to be parallel to 3x minus 2y minus 5. Okay. So a big issue here is that you can't just read off, you can't just say the slope is 3. That would not be correct. Well, let's see that. So first again, we want a point, and the point is given. It's passing through negative 1, 3. And then secondly, we desire a slope. It'll have the same, our slope that we want will have the same slope as this line has. So we have to work with this guy. So the slope, we have 3x minus 2y minus 5 is 0. And then we want to solve for y. So we'll have negative 2y equals negative 3x plus 5. Divide everything by negative 2. So you have y equals 3 halves x minus 5 halves. Okay. So now we can read the slope directly from this equation. And notice now it's 3 halves. Before, if you had just guessed 3, you would have been dead wrong. Sometimes you can get away with that game, and it's a little misleading, but it's usually just luck. If you get it to work, you look here and you say, oh, it's 3, and you go through this, and all of a sudden it is 3. Don't let that, you would need to prove that that would always be the case, and in this case it's not. So you have to do this. I'm telling you, do it. Okay, so I need now to say the slope of this line is 3 halves, and the slope of our line then, which I'll call M2, is the same because they're parallel. So now I can go to my the slope, point slope form. So y minus 3 equals 3 halves times x minus negative 1. Okay. The book this time actually wants you to put it into general form. Okay, so we're not going to solve for y this time. Anyways, y minus 3 equals 3 halves times x plus 1. Okay. To get it in general form, it'll probably be a good idea to get rid of these fractions, because that's what you're going to see in the book. They don't want the fractions. So I'm going to multiply both sides by 2. Okay. So over here you'll have 2y minus 6. Over here you'll have 3. So 2 times 3 halves is 3 times x plus 1. And then I'll have 2y minus 6 equals 3x plus 3. And then I need to get everything on one side, so I'm going to move all of this over, and you end up with 3x minus 2y plus 9 equals 0. You could have also distributed here, so I realize that not everybody would have followed along on this step. If you wanted to, you could have instead just said y minus 3 equals 3 halves x plus 3 halves, and then multiplied through by 2, you know, you're going to get the same thing. Here, 2y minus 6. Over here, the 2's will divide out on each multiple. So you'll end up with 3x plus 3. In other words, you basically just saved yourself a step. So you're getting to the same place is what I'm saying, whichever way you do it. It's just, that was the first way that came into my mind. Okay, let's try one more. Here's number 12. This time, the line we desire passes through the point 5 comma negative 9, and then it's perpendicular to the line x plus 7y minus 12. Okay. So first, again, we need a point. And for these problems so far, it's all been the same. There might be some in the book where you have to do a little work, like they just give you an x-intercept or something. But thankfully, it's just given by negative 9. Secondly, we need a slope. Okay. So again, I'm going to have to take this thing apart and set it y equal to whatever, and then read off the slope. So again, I predict it's not 1. The slope is not what's in front of this x here. You have to maneuver it first. You have to manipulate it. So let's go after it. X plus 7y minus 12 is 0. I'm trying now to isolate y. So we'll have 7y equals negative x plus 12, and then divide through by 7. So y equals negative 1/7 x plus 12/7. And sure enough, it's definitely not 1, right? It's negative 1/7. Okay, the slope of this line then is negative 1/7. So slope 1. We want the negative reciprocal for our new line, so you flip that and make it negative. So it'll be 7 over 1, and then negative negative will be a positive, and that will be our slope. Okay? Okay, so now we go to our point slope form, so I have y minus negative 9 equals 7 times x minus 5. Okay. Y minus negative 9 is y plus 9. And then over here we distribute the 7. So we'll have 7x minus 35. And then I'm going to move the 9 over, so y equals 7x minus 44. Whoops, so we needed this in our general form. That would have been slope-intercept. For general form, I'm going to move the y over. So I'll have 7x minus y, and then minus 44. And that'll be equal to 0. Once I move the y over and subtract the 9 from both sides, you get that. Okay. We study slope extensively through math because it represents a rate of change. And you have rates of change everywhere in nature. So these rates of change sort of just are basically the language of the world in motion around us. And even driving to work, you dealt with rates of change. You dealt with, I drove to work at 50 miles per hour. Whenever you have something like that, when you have a motion involved, it's a rate of change. Okay? So these slopes are actually rates of change, and they're very important in physics and pretty much any biological system you're dealing with. So even with biology, you're thinking, okay, maybe I'll have 3 additional fruit flies per hour, that kind of thing. It's all over the place. It's super important, and it's our next topic. So slopes as rates of change. And we're looking at example 3 in the book. We want to look at the graph in the book, and the graph is about the number of women in millions living alone in particular years. Okay, so we want to find the rate of change going from the year 2000 to the 2013. So in the year 2000, there are 15.5 million women living alone. In the year 2013, there are 18.6 million women living alone. So in order to get the rate of change, what are they really asking for? They're asking for a slope, okay? So you'll find the slope of this. You'll say 18, I'm probably going to need a calculator here eventually, but 18.6 minus 15.5 all over 2013 minus 2000. Okay, so that'll be 3.1 in the numerator all over 13. And as a decimal, it's approximately 0.24. Okay, so we need to know what this number represents. And you can kind of think of it, if you know what these guys are, so this represents millions of women living alone. So we can sort of put that unit in here, women living alone. And down here, this is year, number of years. So what does this represent? Well, it means we have, because it's positive, we have a 3.1 increase, 3.1 million woman increase in number of women living alone every 13 years. This guy over here means we have 0.24 million more women living alone every 1 year. So the trick, at least in my opinion, to interpreting these slopes as rates of change is to kind of embed the units with the numerator and the denominator, and then think of, okay, if this is a positive, it's an increase. If it's a negative, you're going to say decrease. So this is a 0.24 million more women per year increase. So just like when you're driving a car, you're going 50 miles per hour. This is 0.24 million women per year, and you're going more. Okay, so it's increasing. So the book will probably want you to write it out. You want to be able to interpret these. So we'll say there is a 0.24 million increase in the number of women living alone. Per year. Okay. So for linear functions, so for equations of lines, the slope is constant. Okay. You can imagine in this problem here, it probably varies from year to year. So it's not going to be like in 2050. I bet the increase in the number of women living alone per year is not the same as it is in this interval. Okay, so you're going to want to talk about maybe average rates of change instead of some global rate of change. And even more particular, we want more of a variable function for our slope. So that's kind of what the next section is headed towards. And this will make more sense to you if you keep studying math. So we have the average rate of change of a function. And I guess what I'll just go ahead and tell you what I usually tell my calc students is we're very familiar with slopes of lines, right? So the slope of the line at this point is the same as the slope of the line at this point. It has the same tilt across the board, right? Compare and contrast that with this scenario then. So now we have this kind of curvy function which is changing over time. I want to kind of assign some sort of slope to this guy over here and talk about how it's going up and going down, right? So over here, again, the slope is always the same, and you can find it via this formula, y2 minus y1 over x2 minus x1. I want that same idea over here. So how am I going to do it? Well, any point on the curve, you can kind of take what they're going to call a tangent line and put it on the side of that curve, and then talk about the slope of that particular line there. Okay, so the slope of the line here is negative. The slope of the line over here, though, is positive. Okay, so there's different rates of change as we go along this curve. This topic here needs calculus. You need calculus to deal with it because it's called an instant, kind of backwards thought, instantaneous rate of change. It's kind of hard to say, ooh, it's at this particular instant the rate is changing at some value, because if you took a snapshot picture at some particular point, it would just be still. It wouldn't be moving. But that's kind of the craziness of calculus. We'll be after this instantaneous rate of change to describe the slope of functions. Okay. So before we can get there, though, what we're going to do without calculus is talk about average rates of change of these functions. So instead of talking about this tangent line to the curve, what we're going to do is kind of approximate those slopes. Okay. So instead of having this guy right here, maybe we'll take 2 points and then consider this straight line here going through those 2 points. And we can get the formula for the slope of that line. And it's very similar to this formula. I can even call it m, but what we're going to end up calling is just change in y over change in x, which is the slope. That is, from before, if you look back in your notes, that's what we use for slope. But anyways, it's going to be f of x2 minus f of x1 all over x2 minus x1. So some people are like, oh, calculus is so advanced, and it's not. Calculus is really just about, at the beginning, and you'll hear this word derivative, calculus is just about slopes of lines. And you see this formula is really important in calculus, but it really just is the slope formula that we're beating to death right now. Okay. So anyways, that's where this is really getting at, and it's not obvious yet because you haven't progressed enough in math to realize it, but all we're doing is basically trying to apply this idea of slope to a more curvy looking graph. Okay? And then this is a sort of a new slope formula for us. Okay, so enough of that. Let's look at number 14, and we have f of x, our function, equaling 6x. And we want to know its average rate of change from x1 equals 0 to x2 equals 4. And we're using this new formula, but it really is a slope formula. In this case, you're going to find that it gives you the slope. Okay? The answer will be 6. So let's do it. We have f, let's remember what the formula is, f of x2 minus f of x1 all over x2 minus x1. So I'm plugging x2, which is 4, into this function. So I'll have 6 times 4 is 24, minus f of x1, so 6 times 0, which is 0, all over x2, which is 4, minus x1, which is 0. So that would be 24 over 4, which is 6. And sure enough, if you remember your slope-intercept form, the slope is 6. And that's what we have here. Okay? You got the same answer that you would expect to get. So let's then talk about a nonlinear function, right? And this is, if you looked at the graph, it would be curvy, right? In particular, it would be a parabola. We want to look at the slope going from x1 equals 3 to x2 equals 6. It's the same spiel. Let's use the other notation, change in y over change in x, instead of slope this time. So f of x2, so I'm plugging 6 into this formula. So 6 squared minus 2 times 6. Minus f of x1, so that'll be 3 squared minus 2 times 3. All over x2 minus x1, so 6 minus 3. 6 squared is 36 minus 12 minus 9 minus 6 all over 3. Keep going. 36 minus 12 is 24. Minus 9 minus 6 is 3 again. So I have 21 thirds. In other words, the slope at that point is 7. Okay. We can actually graph this thing. I'll find its intercept. So it'd be x times x minus 2 is 0. Its vertex, we'll recall those formulas here later, but the vertex, the x-coordinate of the vertex, which we usually call h, negative b all over 2a, so 2 all over 2 times 1 is 1, and then plug 1 back in there, so k would be 1 minus 2, which is negative 1, so 1, negative 1 here, the intercept's at 0, and then 2, so the graph looks like this. And then 3, 4, 5, 6. So, what they're looking for is the slope of the line that connects these two dots here. And you see that, I guess this isn't a very good example, but the line that connects these two dots would be like this. And what this formula is telling you is that the slope of this line that connects those dots is 7. Okay? And it basically approximates the tilt of the graph in this region. Okay? So it has upward, it's rising and through that region. Okay. Certainly there will be some story problems associated with this. Let's look at example 5. So find the average rate of change on the graph, and we're talking about the concentration of a particular drug in the system over a certain amount of time. So you take a drug like maybe Xanax or something, and how much Xanax is going to be in your blood system after 4 hours, that sort of idea. So find the average rate of change from time equals 3 hours to time equals 7 hours. So especially with something like Xanax, there might be a lot in your system at first, and then it'll go away very fast and then kind of taper out. So I'm not exactly sure what I don't have the graph on me, but you can imagine it's going something like this over time. And we want to know sort of the average rate of change going from hour 3 to hour 7. Okay, so the book will give you some points. So you're given the point 3, 0.05 and 7, 0.02, where this is the time, and this thing represents the number of, I guess it's in milligrams. Milligrams per 100 milliliters. I'm not even sure at this point what the story problem is about, and I don't want to get up and go get my book because it's going to take 20 minutes. And all right, so basically it's just a slope problem again, but it's this weird new slope that we have. So let's remind ourselves what that slope is. It's f of x2 is basically just y2 minus y1 all over x2 minus x1, and in this particular case, f of x2 then is this guy, 0.02, f of x1 is this guy, 0.05, and then x2 is 7, and x1 is 3. If you put it in your calculator, you get negative 0.0075, and then we want to interpret that as average rate of change. So the concentration of the drug in this case we are decreasing because of the negative, decreases by 0.0075 milliliters per milliliters, 0.075 milligrams per 100 milliliters per every hour. So I'll just say for every hour. So again, you want to think of embedding the units in the numerator and denominator. In the numerator, that represents milligrams per 100 milliliters, and the denominator is representing hours. Okay, so there's that. In physics, then, we'll be worried about velocity. So we want to talk a little bit about that. So your average velocity. And if you're given positions over per position, like I'm over in North Olmsted at time 7 o'clock, and then I'm in Parma at 7:20. If you know that information, you could get velocity, which is a kind of a cool thing. So the average velocity, and we're going to use the letter S for change in position. This will be your average velocity. Okay, so it's change in position over change in time. Okay, so 26, we kind of have a famous kind of problem that people studied a lot back in the day, and it's a ball rolling down a ramp. They give you a function to represent the position of the ball with respect to time. So that function is S of t equals 12t squared. Part A, they want you to find the average rate of change from, or the average velocity in this case, going from t1 equals 3 to t2 equals 4. Right? And what is that? Well, it's just slope again. Okay, so maybe if nothing else, the takeaway here is that slope is just literally all over the place in our sciences. So anyways, so we'll have 12 times 4 squared minus 12 times 3 squared. So again, this is our formula, f of, or in this case it would be s of t2 minus s of t1 all over t2 minus t1. So we have this all over 4 minus 3. 16 times, let's just factor out the 12, so we'll have 16 minus 9 all over 4 minus 3 is 1. 16 minus 9 is 7. 7 times 12 is 84. And then if you embed the units, so we have some distance for every time unit. And the distance is in feet here, and the time unit is in hours, or seconds, sorry. So 3 seconds to 4 seconds. Right, so at the end of the day, the ball is rolling 84 feet per second at this particular time. During this time interval. Okay, so let me just again just mention then, if you have some sort of ramp and then the ball is rolling down the ramp, you can expect that as the ball first starts falling, it's going to have a much higher rate of change compared to over here. If you go on to over to Cedar Point or something like that, you'll see that, right? The Grand, what the heck is the dragster when it goes flying up and then it comes back down. You're going really fast at first, and then you slow down as you come back into the docking area. Okay, so you consider average rates of change. How fast am I going down here? How fast am I going up here? That's kind of what we're getting at. There's different slopes. Okay, I think that's it for this section.